Next speaker is Dr. Laura Kreidberg. Laura received her PhD from the University of Chicago a few weeks ago. She is moving on to Harvard and the CFA this fall.
Okay, thanks. All right, can you hear me? Okay, so as a representative of the observers, I'm here to push back against what Caitlin just said about how we can't learn anything about planet formation from studying atmospheres. I primarily study transiting planets, and I use high precision HST and Spitzer data to learn as much about them as I can. But before I get into that, I want to start with an advertisement. This is, so the Batman package is a Python code that I wrote to calculate model transit light curves. I think this is censored because I used it in my defense talk. They calculate badass transit light curves. It implements a new integration algorithm that I developed to handle any radially symmetric stellar limb darkening law. It's written in Python with C extension modules, and it's parallelized with OpenMP, so it runs really fast. So if ever in the future you or your friends or your grandmother need to model a transit light curve, check out this package. So a number of people have showed flowcharts describing the work that they do, and I decided I would make my own. So I start with photons. And from those, I measure complex physics and chemistry in 3 dimensions for planets hundreds of parsecs away. And I didn't put this on there, but we also learn about how they formed from these measurements. And the way I do this is by magic. Actually, no, really what happens is I email my client a lot. And I'll just leave that there for a minute. Mike. I will say, Mike, I had a version where I had your head and my head, so it was this like 2-headed monster thing. So it could be worse, and you could really consider this for your hairstyle, Okay, so I want to start with a particular example to illustrate sort of the state of the art of these measurements, as well as the kinds of questions we're trying to address. And I know that most of you are theorists, and so you don't care about the phone numbers of these planets, but I'll just say WASP-12 is one of the most studied hot Jupiters. It has a very short orbital period, so it's one of the most highly irradiated planets known. And it's famous because of this result from about 5 years ago now by Madhu, where he took a measurement of the planet's thermal emission spectrum from Spitzer and inferred that the atmosphere has a carbon-rich composition. Where's the laser? Is it here? Okay. So, and this inference is really hinging on this data point right here with the black arrow. This is the Spitzer 4.5 micron bandpass. And it's not resolving any individual molecular absorbers because it's a broad bandpass about a micron wide. But Madhu did one of the earliest retrievals and found that in order to explain that dip in the spectrum there, you have to have an overabundance of methane and an underabundance of water from what you would expect for thermochemical equilibrium. And this can be explained if you have a carbon to oxygen ratio greater than unity in the planet's atmosphere. And this is really interesting from the standpoint of planet formation. And I think this same slide was shown by Jonathan or somebody a couple days ago. But I'll show it again because it's important. And the idea here is, so this is showing the carbon to oxygen ratio in gas with the black line, the solid line, and in grains with the dashed line. And the idea is that as you move away from the host star, you have a gradient in the chemistry, and you get water freezing out here, and the gas becoming preferentially carbon-rich because all the oxygen has frozen out in water. And so if you have a carbon-rich hot Jupiter atmosphere, that suggests perhaps that it formed beyond the water ice line where the gas is carbon-rich, and as it accreted a lot of that gas, you ended up with more carbon in the atmosphere than you would expect relative to the composition of the host star. And somewhat amazingly, this result has really stood the test of time. This is the most recent analysis of the planet's emission spectrum from Kevin Stevenson, and it incorporates additional data, better modeling techniques, more sophisticated treatment of the atmospheric chemistry. And I'll highlight here, this is a spectrum from the Wide Field Camera 3 on HST, It covers the wavelength range from about 1.1 to 1.7 microns. And in that wavelength range, the dominant absorber is water. But you'll note that there are no visible absorption features here. It's consistent with the blackbody spectrum. And so that's confirming this idea that the planet is carbon rich. Okay, so it's sort of hard to overstate how important WASP-12 has been in the development of the field, because it's motivated measurements of the carbon to oxygen ratio for additional planets, measurements of C/O for exoplanet host stars, and a huge amount of theoretical work to understand the chemistry in carbon-rich atmospheres. And so what I did was I took a complementary observing approach to study the planet's composition in more detail. And I measured a transmission spectrum. This is again from HST with C3, from a total of 6 transit observations all stacked. And what you'll see is there's a very prominent absorption feature here that is due unambiguously to water. And just to brag a little bit, this is our data in the context of other high precision measurements that have been obtained so far. So the spectrum I measured is the black data. And the error bars are actually on there, but they're so small that it's hard to see them. And I'm illustrating this because I want to emphasize that the kind of work that I'm doing is really a preview of the sorts of measurements that we want to make with JWST. And it's really interesting to see what kinds of physics and chemistry we can learn about at this very high signal to noise. So here's the spectrum again. So this is great. This is the first time we have unambiguously identified a molecular species in the atmosphere of WASP-12. So we should all be celebrating, right? Yes? Well, so thanks, John. This is from this past December. We were all in Hawaii for Extreme Solar Systems, and I wanted like a reaction shot. And this is what happened. And I want to just like emphasize for a minute. This is Jonathan. This is the best impersonation of the scream that I've ever seen. I'll just leave that there for a second too, Jonathan. You're a good sport. Okay, I'll take it down now. So what is the problem here? Well, the idea is that in carbon-rich chemistry, you would not expect water to be abundant. And I'm illustrating why in this plot here. So this is the water abundance on the y-axis and the atmospheric temperature on the x-axis. And in predictions from equilibrium chemistry, shown with the shaded regions. And the idea is that for carbon-rich chemistry, most of the oxygen is bound up in CO and CO2, and so there's none left to form water. However, our data point is right here. And I'll spare you all the gory details, but Mike and I really worked on this, and we found that a carbon-rich composition is conclusively ruled out by the measurement that we made. Okay, so this is bad. So WASP-12 is like the easiest target to study. We have the highest precision data both in the thermal emission spectrum and the planet's transmission spectrum from HST and Spitzer. And we have attacked it with our most sophisticated theoretical models to try to understand the composition of the atmosphere. And we get totally different answers. And so I have some ideas about why that might be, but I'm going to leave it as a cliffhanger for now and instead give the observer's answer, which is to say, oh, of course, what we need to do now is get more data. Because the transmission spectrum and the dayside thermal emission spectrum are not all that we can measure. And so I want to just describe now an alternative measurement approach that we applied to a different hot Jupiter. This one is WASP-103b. I know you're all going to remember that later. And for this planet, we did a novel kind of measurement. We observed a thermal phase curve for the planet over 3 complete orbital revolutions. Its orbital period is about a day. And this is the first time this has ever been done with HST. And this is the band-integrated thermal phase curve, but we actually can break it up into spectroscopic phase curves like this. So they're shown, lying on their sides on the top panel. And what we can do with this is measure the phase-resolved thermal emission spectrum of the planet. So you can see as the dayside rotates into view, you have higher flux. There's a prominent water absorption feature here. But the really powerful aspect of this data set, I could talk about this for an hour, but because I have how many more minutes? Like 5? A couple. 5.5. Okay. The real advantage of this type of data set is that you can use it to constrain the planet's global thermal structure. And I have a movie to illustrate this here. And I should say this is all work done by Kevin Stevenson. So on the top panel, I'm showing a very much interpolated emission spectrum as a function of orbital phase. In the top right, I'm showing the TP profile that we retrieved from these data. And on the bottom, I'm showing some representative brightness temperature maps at 3 different wavelengths. So the middle one is in the middle of the water band at 1.4 microns. And so the planet is fainter at those wavelengths because we're observing higher up in the atmosphere. And so this is a tremendously powerful technique in constraining the 3D thermal structure of the planet's atmosphere. We can compare this with GCM modeling to check and see whether such a complicated thing to solve is actually coming out correctly, and it turns out that it is. I don't have a slide showing this, but Tiffany Kataria ran her GCM and compared it with our phase resolve spectra and had very, very good agreement. And so what I'm doing, and one of the things I'm going to be working on this summer, is making the same kind of measurement for a different planet. This one is another very short period hot Jupiter. And this is a special one because it's very similar in temperature to WASP-12. It's orbiting a similar spectral type host star, similar orbital period, similar surface gravity and radius. And so we can really start to begin doing comparative planetology between these objects to really learn what's going on. And here's a preliminary result. This is the WFC3 band integrated phase curve. And you can see that it looks quite similar to what we measured for WASP-43. But if you look at the dayside spectrum, it's pretty different. So WASP-43 had a very strong water absorption feature, but WASP-103 does not. The predictions for what we would expect from a 1D TP profile, you'd expect a big water absorption feature right here, and that's not at all what we see. And so there's a couple different explanations for this. One is that the planet's atmosphere is carbon rich, just like what was proposed for WASP-12. Alternatively, it could have no metals in its atmosphere, be very metal depleted, and then you wouldn't see absorption features either. But a third possibility is that the atmosphere is simply isothermal over the pressure levels that we're probing. And because we have, we'll be able to measure the full 3-dimensional thermal structure of the atmosphere, we can learn whether such an isothermal TP profile is a natural outcome of the dynamics, or whether one of these other possibilities is correct. And this will help us understand what's happening with WASP-12 as well. So, right, skip that. And the last thing, okay, so here we go. So here's WASP-103, here's WASP-12. And what I hope to be able to do this summer is compare the thermal structure of WASP-103's atmosphere and use that to predict what the temperature pressure profile should be for WASP-12 to see whether we can start to reconcile the disagreement in the results between the transmission spectrum and the dayside emission spectrum for this planet. So I want to talk about another very preliminary thing that I'm going to be working on this summer, and this is a technique that we can use to actually learn about the latitudinal temperature structure of the atmosphere of a planet. And this has not been done that much. The technique is called eclipse mapping. And what you do is you measure a very, very precise eclipse light curve for the planet. And I'm showing just the ingress and egress here. That's why it looks so weird. And if you have an asymmetric distribution of brightness on the planet's photosphere, that can show up as anomalies in the shape of the phase curve. And you can then retrieve the latitude and the longitude of the hotspot on the planet. And so I have a data set to do this. This is for yet another hot Jupiter, WASP-18b. And we also have a spectroscopic phase curve from HST. And so what I hope to do with this is make a map of the thermal structure as a function of latitude, longitude, and altitude, and yes, latitude, longitude, and altitude. So the first 3D weather map of a planet. And that's something that I'll be working on while I'm here. And if you're interested in talking to me about that, please do so. I think I'm out of time, so I'll wrap up. Thank you. With it, so it doesn't actually matter. So limb darkening is only relevant for the transit. Yeah, that's okay. Yeah, right. But that would probably be a smaller effect than this, because we're most sensitive to the very brightest spot in the atmosphere. Yeah. For which? For WASP-12? I don't remember. I can send you the paper. Less than 100 ppm for sure, though. Probably about 50 per channel. Yeah. So it was two things. One is that we observed more transits by a factor of 6. The other thing is that we observed with this new mode called spatial scanning that Jacob talked about this morning, and that gives you a much better duty cycle for the observations, and so you collect a factor of, several, at least, more photons per transit.